Hey there, how was your day? Wherever you are in the world, whatever time it is, I'm glad you're here. Tonight we're going to embark on a journey so vast, so impossibly distant that it challenges everything we think we know about the future of existence itself. What would you see if you could travel 1 billion years into the future? What would remain of our planet, our solar system, our very reality? In this gentle exploration, we'll drift through deep time itself, witnessing transformations so profound they reshape the very meaning of permanence. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination carry you across eons of cosmic time. I would love and encourage you to watch this journey to its end to discover the breathtaking vistas that await, but there is absolutely no problem if you doze off along the way. Let your thoughts float across the centuries like whispers in the cosmic wind, a gentle request that if you find comfort in these explorations of deep time, I'd be grateful if you'd consider subscribing and liking this video. It helps others find these quiet contemplations of our cosmic future. Also, I'd love to know where you're listening from tonight. Feel free to comment your time and location below. There's something beautifully humbling about contemplating the far future while scattered across our small planet, each of us experiencing this moment under the same sky that will witness transformations beyond our wildest imagination. Let's begin this journey into the deep future, where time itself becomes our vessel, and wonder our compass. You're standing in your backyard on a quiet evening, feeling the familiar weight of gravity beneath your feet, breathing air that has sustained life for billions of years. Now imagine that same spot, that exact location where you stand, but 1 billion years from now. What would you find there? What would remain of everything you know? This isn't science fiction. This is science itself, peering forward through the mathematics of stellar evolution, geological processes, and cosmic mechanics to paint a portrait of Earth's far future that is both beautiful and haunting. Because here's what most people don't realize about deep time. 1 billion years isn't just a long time. It's a span so vast that it dwarfs the entire history of complex life on Earth. Think about this. 1 billion years ago, the most sophisticated life forms on our planet were simple bacteria and algae. There were no animals, no plants, no forests, no eyes to see or minds to wonder. The oxygen in our atmosphere was still building up from ancient cyanobacteria. Complex cells had only recently learned to work together. Everything we associate with life on Earth, from the first fish to the dinosaurs to human civilization, has unfolded in less than 1 billion years. Now, we're asking, what happens in the next billion? We're peering forward across a chasm of time that spans the entire evolutionary journey, from microbes to consciousness. And what we discover is that this journey into the deep future reveals something profound about the nature of change itself. The first thing you would notice in our billion-year future is the sky. The sun, that steady companion that has warmed our world for over 4 billion years, has been slowly growing brighter throughout its life. This isn't a sudden change, but a gradual transformation, written into the very physics of stellar evolution. As hydrogen fuses into helium in the sun's core, the star becomes more luminous, more energetic, more intense. In 1 billion years, the sun will be roughly 10% brighter than it is today. 10% might not sound dramatic, but in the delicate balance of planetary climate, this increase is catastrophic. The additional energy will trigger a runaway greenhouse effect that will fundamentally transform our world. The oceans, those vast blue expanses that have defined Earth for billions of years, will begin to boil away into space. Imagine standing on that future Earth and looking up at a sky devoid of the familiar blue we've known throughout human history. Instead, you would see a harsh, brilliant dome of superheated steam and vapor. The water cycle that has shaped weather, carved landscapes, and sustained life will have broken down completely. Rivers will have long since evaporated. Lakes will exist only as salt flats and dried basins. The polar ice caps will be nothing but memory. But the story of water's departure is more complex and beautiful than simple boiling. As temperatures rise and the atmosphere fills with water vapor, something remarkable happens. Water vapor rises high into the atmosphere, where ultraviolet radiation from the sun breaks it apart into hydrogen and oxygen. The lightweight hydrogen escapes to space, lost forever, while the oxygen remains behind. Earth's atmosphere will become incredibly oxygen-rich, creating conditions unlike anything in our planet's history. This oxygen-rich atmosphere will have profound effects on any remaining geology. Rocks will oxidize at accelerated rates. The familiar colors of landscapes will shift toward rusty reds and brilliant oranges as iron compounds react with the abundant oxygen. The very ground beneath your feet will tell the story of water's departure through its transformed chemistry. Yet, even as the familiar Earth disappears, new forms of beauty emerge. Without water to moderate temperatures and create weather patterns, the planet's surface will become a realm of extremes. Of degrees. While nightside regions' ice-side temperatures may soar to hundreds, could remain relatively cooler, creating temperature gradients that drive winds of incredible power across the barren landscape. The moon, our ancient companion, will still hang in the sky, but it too will have changed. Over the course of 1 billion years, the gradual recession of the moon will have continued. Each year the moon moves about 3.8 semi-hours farther from Earth as tidal interactions slowly transfer rotational energy. After 1 billion years of this process, the moon will appear noticeably smaller in the sky, and its gravitational influence will be weaker. This changing relationship between Earth and Moon will have affected the planet's rotation. Earth's day will have grown longer, perhaps lasting 30 or 40 hours instead of our familiar 24. The slower rotation will create different patterns of atmospheric circulation, different rhythms of heating and cooling, different ways that energy moves around the planet. But what about life? Could anything survive this transformation? The answer reveals something remarkable about the tenacity of biology. While complex surface life will have long since vanished, certain forms of life might persist in unexpected places. Deep underground in caves and rock formations far from the surface heat, communities of bacteria and archaea might continue to thrive. These extreophiles, organisms that live in conditions we would consider impossible, represent life's last stand on a transforming world. These underground ecosystems will have evolved in isolation for hundreds of millions of years, possibly developing into forms we can barely imagine. Without sunlight, they will depend entirely on chemical energy from rock interactions, radioactive decay, and geothermal processes. They might represent an entirely new branch of life's tree, as different from current organisms as current organisms are from the earliest bacteria. The geological story of this future Earth is equally fascinating. Without water to drive erosion and weathering, the processes that shape landscapes will operate differently. Wind erosion will continue, but without the moderating effects of vegetation and water. It will carve the land in new ways. Ancient mountain ranges will be slowly ground down, while new formations created by thermal expansion and contraction emerge. Volcanic activity will continue, possibly intensified by the changing thermal conditions. These volcanoes will release gases and minerals into the atmosphere, contributing to the planet's evolving chemistry. The dance between geology and atmosphere that has operated throughout Earth's history will continue. But according to new rules written by the absence of water, the polar regions once defined by ice and snow will become landscapes of exposed rock and ancient sediments. The geological record of Earth's watery past will be laid bare, creating a kind of museum of planetary history written in stone. Future visitors, if any exist, could read the story of oceans and rivers in the stratified rocks like pages in a book describing a world that once was. Yet, even as we contemplate this transformed Earth, we must remember that 1 billion years is time enough for surprises. The history of our planet is filled with unexpected events that have reshaped everything. Asteroid impacts, supervolcanic eruptions, changes in solar output, and even the effects of nearby stellar events could alter this trajectory in ways we cannot predict. There's something both humbling and beautiful about contemplating these vast timescales. They remind us that change is the only constant, that even the most permanent-seeming features of our world are temporary arrangements in the long dance of cosmic evolution. The mountains we consider eternal will be worn away. The oceans we think of as everlasting will boil into space. Yet new forms of order and beauty will emerge from these transformations. As we continue our journey through this billion-year future, we'll explore what happens beyond Earth, to our solar system, to the stars themselves. We'll discover how the story of our transformed planet fits into the larger narrative of cosmic evolution. And we'll contemplate what it means for consciousness, for meaning, for the possibility of life itself in a universe that never stops changing. But for now, as you rest here contemplating these vast transformations, remember that you are part of this story. Every breath you take connects you to the atmosphere that will one day escape to space. Every step you take touches ground that will one day be transformed beyond recognition. You exist in a brief, beautiful moment in the long history of change. a conscious observer in the ongoing dance of matter and energy that we call existence. The billion-year future awaits, vast and strange and wonderful, and we have only just begun to explore its mysteries. Beyond our transformed Earth, the solar system itself will have undergone changes that would render it nearly unrecognizable to our eyes. The dance of planets that has maintained its rhythm for billions of years will continue, but with subtle variations that accumulate into profound differences over such vast timescales. Mars, that rust-cold neighbor we've dreamed of visiting, will have evolved in its own quiet way. Without the moderating influence of a thick atmosphere or abundant water, Mars changes slowly, but change it does. The planet's thin atmosphere will have continued its gradual escape to space, molecule by molecule, year by year. After a billion years of this patient exodus, Mars will be even more airless than it is today, its surface pressure dropping to levels that make our current Martian atmosphere seem thick by comparison. The polar ice caps of Mars, those seasonal deposits of frozen carbon dioxide and water, will have undergone countless cycles of growth and retreat. But the overall trend will be toward diminishment, as the planet's already tenuous grip on its atmosphere weakens further. The great dust storms that occasionally engulf the entire planet will become rarer. Not because the winds have calmed, but because there's simply less atmosphere to carry the dust. Yet Mars holds secrets that a billion years will slowly reveal. Deep beneath its surface, in caverns and rock formations we've never imagined, processes will continue that might surprise us. The planet's core, still warm from its formation, and the decay of radioactive elements, will continue to drive subtle geological activity. Occasional volcanic eruptions might still punctuate the Martian silence, releasing gases that briefly thicken the atmosphere before they too escape to space. Jupiter, that massive guardian of the outer solar system, will maintain its stately presence. But even this giant will show signs of deep time's passage. The Great Red Spot, that storm larger than Earth itself, may finally dissipate after raging for centuries or millennia beyond our current era. New storms will form and fade, each lasting for spans of time that dwarf human civilization, yet appearing as mere moments in Jupiter's billion-year story. The moons of Jupiter will continue their intricate orbital dance, but tidal forces will have subtly reshaped their paths. Europa's icy surface will have been renewed countless times as its subsurface ocean continues to interact with the rocky core below. If life exists in those dark waters, it will have had a billion years to evolve in isolation, potentially developing into forms as different from Earth life as we can imagine. Jupiter's volcanic moon will have exhausted more of its internal heat, though sulfur volcanoes may still paint its surface in brilliant yellows and oranges. The constant gravitational kneading from Jupiter will continue, but perhaps less vigorously, as the system slowly loses energy to gravitational waves and tidal friction. Saturn's rings, those magnificent bands of ice and rock that have captivated human imagination, present one of the most poignant stories of our billion-year future. These rings are not permanent fixtures, but temporary decorations in cosmic terms. Current estimates suggest they formed relatively recently, perhaps only a few 100 million years ago, and they won't last forever. Over the course of a billion years, Saturn's rings will gradually spiral inward, consumed by the planet's gravity and magnetic field. The process is slow but inexorable. Ring particles collide and lose energy, causing them to drift toward Saturn. Some will be absorbed by the planet's atmosphere, while others will be swept up by the many small moons that orbit within the ring system. Future observers looking at Saturn and our billion-year destination might see only faint remnants of the spectacular ring system we know today. Perhaps a few tenuous bands will remain, or maybe the rings will have vanished entirely, leaving Saturn as just another gas giant without its distinctive crown. The thought carries a strange melancholy, like imagining a future where no one remembers the sound of rain. But Saturn may compensate for this loss with new wonders. Its moon Titan, with its thick atmosphere and lakes of liquid methane, will continue evolving its own unique chemistry. The interplay between Titan's atmosphere, surface, and subsurface ocean creates a complex system that could surprise us with new developments over such vast timescales. Uranus and Neptune, those distant ice giants, will maintain their lonely vigil at the edge of our solar system. Their positions will have shifted slightly due to gravitational interactions with other planets and passing stars, but these changes will be subtle. What's more interesting is how their internal heat sources will have evolved. Both planets radiate more heat than they receive from the sun, and this internal warmth will continue to drive weather patterns and atmospheric dynamics across our billion-year time span. The Kuiper Belt, that vast collection of icy bodies beyond Neptune, will have been sculpted by countless gravitational encounters. Some objects will have been scattered inward toward the sun, creating spectacular comets that briefly illuminate the inner solar system before fading. Others will have been flung outward into the even more distant Oort cloud, or lost to interstellar space entirely. Perhaps most remarkably, our solar system will have encountered other stars during its billion-year journey around the galaxy. The Sun, along with all its planets, orbits the center of the Milky Way, once every 225 million years. In a billion years, we will have completed more than 4 full galactic orbits, passing through different regions of space, encountering different stellar neighborhoods. During these travels, other stars will have approached our solar system, some coming close enough to perturb the orbits of comets in the Oort cloud, or even affect the outer planets' trajectories. These stellar encounters, while rare, could dramatically reshape the architecture of our solar system. A close pass by another star might scatter comets throughout the inner system, creating a prolonged period of bombardment. Alternatively, it might strip away some of our system's most distant objects, stealing them into interstellar space. The Sun itself will tell the most dramatic story of transformation over this time span. As we've seen with Earth's changing climate, the Sun's gradual brightening will affect all the planets. Mars might briefly experience a renaissance as increased solar heating could theoretically release gases from its polar caps and subsurface reservoirs, creating a temporary thickening of its atmosphere. Venus, already hellishly hot, will become even more extreme as the enhanced solar output drives its greenhouse effect to new heights. But beyond these planetary effects, the Sun's evolution will manifest in ways both subtle and profound. Solar flares and coronal mass ejections will continue to erupt from its surface, but their character may change as the Sun's magnetic field evolves. The solar wind, that constant stream of charged particles flowing outward from our star, will intensify, gradually stripping away more of the planetary atmospheres and affecting the magnetic fields of worlds throughout the system. The asteroid belt between Mars and Jupiter will continue its slow evolution, with collisions gradually grinding large asteroids into smaller fragments. Some of these fragments will eventually spiral inward toward the Sun, while others will be captured by planetary gravities or flung outward. The belt will become more diffuse over time, though it will never disappear entirely. Throughout all these changes, the fundamental physics that governs our solar system will remain constant. Gravity will continue to orchestrate the dance of worlds. Electromagnetic forces will shape planetary magnetospheres, and thermodynamics will drive the flow of energy from hot to cold. Yet within these unchanging laws, endless variations will play out, creating new configurations, new relationships, new possibilities for beauty and complexity. As we contemplate this transformed solar system of our billion-year future, we begin to appreciate the true nature of cosmic time. What seems permanent to us, the arrangement of planets and moons we see in our night sky, is actually just a momentary configuration in an endless dance of gravitational interactions. The solar system is not a static mechanism, but a living, evolving entity that will surprise us with new developments even across the vast spans of deep time. And yet, for all these changes, something will remain recognizably familiar. The Sun will still shine, though more brightly. Planets will still orbit, though along slightly different paths. The basic architecture of our cosmic neighborhood will persist, even as its details transform beyond recognition. This persistence within change, this continuity within transformation, hints at something profound about the nature of existence itself. Even as we prepare to explore what lies beyond our solar system in this billion-year future, we carry with us the understanding that change and permanence are not opposites, but partners in the cosmic dance that connects every moment to eternity. As we venture beyond our transformed solar system, we encounter changes so vast, they challenge our understanding of permanence itself. The stars, those eternal beacons that have guided human navigation and imagination since our species first looked upward, will have undergone their own profound transformations across this billion-year span. The constellation patterns that have remained relatively stable throughout human history will have shifted noticeably. Stars move through space at different velocities, and over a billion years, these proper motions accumulate into visible changes. The Big Dipper will no longer resemble a ladle. Orion's belt will have scattered. The Southern Cross will have drifted into new configurations. Future observers, if they exist, will see an entirely different tapestry of stellar patterns painted across their night sky. but the changes run far deeper than mere stellar rearrangement. Many of the stars visible in our current night sky will have completed their life cycles entirely. Massive blue giants, those spectacular but short-lived stellar torches, will have long since exhausted their nuclear fuel and died in supernova explosions of unimaginable violence. These cosmic detonations will have scattered heavy elements throughout space, seeding future generations of stars and planets with the materials necessary for complexity. Some of these stellar deaths will have occurred relatively nearby, close enough to affect our solar system directly. A supernova within 50 light-years could strip away portions of our outer planet's atmospheres or trigger climate changes even on our already transformed Earth. The radiation from such explosions might briefly illuminate our solar system with ghostly auroras, painting the sky in colors we've never seen. Other stars will have evolved more gradually. Sun-like stars in our neighborhood will have swollen into red giants before shedding their outer layers and collapsing into white dwarfs. These stellar remnants, incredibly dense cores no larger than Earth, but containing the mass of an entire star, will dot the galaxy like cosmic lighthouses, slowly cooling over timescales that dwarf even our billion-year journey. The galaxy itself will have rotated, carrying our solar system through different regions of space. We will have passed through spiral arms, those regions of enhanced star formation where massive young stars illuminate vast clouds of gas and dust. During these passages, the night sky will have blazed with nebula of extraordinary beauty, stellar nurseries where new suns are born from the gravitational collapse of interstellar material. Between these spiral arms, our solar system will have traversed quieter regions of space, cosmic suburbs where stars are more widely separated and the interstellar medium is thinner. These periods will offer different perspectives on the galaxy, different views of distant star clusters and nebulae, different exposures to cosmic radiation and interstellar particles. Throughout this galactic journey, our solar system will have encountered the invisible presence of dark matter, that mysterious substance that outweighs ordinary matter by 5 to 1. While dark matter rarely interacts with normal matter except through gravity over billion-year timescales, even these weak interactions could subtly influence planetary orbits and the behavior of comets in our system's outer reaches. The Milky Way itself will be preparing for its own grand transformation during this epoch. Our galaxy is currently on a collision course with the Andromeda Galaxy. And while this cosmic merger won't begin in earnest for another 4 billion years, the gravitational effects will become increasingly noticeable during our billion-year time frame. Tidal forces between the two galaxies will begin to distort their spiral structures, creating streams of stars and gas that stretch across hundreds of thousands of light-years. This approaching merger will affect star formation rates throughout both galaxies. Gravitational interactions will compress gas clouds, triggering bursts of stellar birth that will illuminate the cosmic landscape with brilliant young stars. Simultaneously, some existing star systems will be scattered into the intergalactic void, becoming cosmic nomads traveling through empty space between galaxies. But perhaps the most profound changes will be occurring on scales we can barely perceive. The fabric of space-time itself will be rippling with gravitational waves, those distortions in the geometry of reality created by accelerating masses. Over 1 billion years, these waves will carry away energy from orbiting systems throughout the galaxy, causing binary stars to spiral inward and eventually merge in spectacular displays of gravitational radiation. Some of these mergers will involve neutron stars, those incredibly dense stellar remnants where a teaspoon of matter would weigh as much as a mountain. When neutron stars collide, they create kilonova explosions that forge heavy elements like gold and platinum, scattering these precious materials throughout space. The universe will have experienced thousands of such events during our billion-year span, gradually enriching the interstellar medium with the building blocks of complexity. Black holes, those regions where gravity has become so strong that not even light can escape, will continue their patient consumption of surrounding matter. Some will have grown substantially, feeding on gas and dust and occasional stellar companions. Others will remain quiescent, invisible except for their gravitational influence on nearby objects. The supermassive black hole at the center of our galaxy will continue orchestrating the dance of stars in the galactic core. Its 4 million solar masses, mass presence shaping the evolution of our cosmic neighborhood. Yet even as we contemplate these vast scales and cosmic transformations, we must remember that 1 billion years allows time for the unexpected. Gamma ray bursts from distant galaxies might bathe our region of space in high-energy radiation. Nearby star formation might create massive stellar associations that alter the local environment. Rogue planets ejected from other star systems might pass through our cosmic neighborhood, briefly disturbing the gravitational balance we've known for so long. The interstellar medium itself, that thin soup of gas and dust between the stars, will have been stirred and mixed by stellar winds, supernova explosions, and the passage of our solar system through different galactic regions. New chemical combinations will have formed in the cold darkness of space, creating complex organic molecules that drift through the void like seeds, waiting for the right conditions to flourish. Perhaps most remarkably, this billion-year span will have allowed time for entirely new forms of stellar evolution to manifest. Stars that are just beginning their main sequence lives today will have burned through significant portions of their hydrogen fuel. Binary star systems will have exchanged mass, creating exotic configurations we can barely imagine. White dwarf stars will have accreted material from companions, possibly triggering nova explosions that briefly outshine entire galaxies. The cosmic web itself, that vast network of dark matter filaments that connects galaxy clusters across the universe, will have evolved subtly but significantly. Structure formation will have continued on the largest scales, with galaxy clusters merging and growing while voids between them expand and empty. Our local group of galaxies will have shifted position within this cosmic architecture, changing our perspective on the distant universe. Throughout all these transformations, the fundamental constants of physics will have remained steady. The speed of light will still define the maximum rate of information transfer. Gravity will continue to attract mass and energy according to Einstein's equations. Quantum mechanics will still govern the behavior of particles on the smallest scales. Yet within these unchanging laws, endless creativity will have manifested, producing new arrangements of matter and energy that we cannot yet imagine. This is the context within which our transformed Earth and solar system exist in the billion-year future. We are part of a vast, interconnected cosmic ecosystem, where changes on one scale influence developments on all others. The death of a massive star enriches the interstellar medium that will someday form new planets. The merger of galaxies creates conditions for enhanced star formation. The slow evolution of the universe itself provides the stage upon which all these dramas play out. As we continue our journey through this deep future, we begin to understand that transformation is not something that happens to the universe. It is what the universe is. Every moment brings new configurations, new possibilities, new expressions of the creative potential inherent in the fundamental laws of nature. The billion-year future is not a destination, but a continuing journey, an ongoing exploration of what is possible when matter and energy dance together across the vast expanses of space and time. And somewhere in this transformed cosmos, in this galaxy reshaped by eons of change, our little solar system continues its ancient orbit, carrying with it the story of a small blue planet where consciousness once arose and dared to wonder about its place in the grand symphony of existence. Looking deeper into this billion-year canvas, we discover that the very atoms that compose everything around us will have embarked on journeys of their own. The carbon in your body, forged billions of years ago in stellar cores, will have cycled through countless forms during this vast span. Some atoms will have been locked in crystalline structures deep underground. Others will have drifted through space as cosmic dust, riding stellar winds between star systems. Still others will have been incorporated into new worlds, new atmospheres, new possibilities for complexity. The recycling of matter operates on timescales that humble our understanding of permanence. Every handful of Earth contains atoms that have witnessed the birth and death of stars, the formation and erosion of mountains, the rise and fall of countless atmospheric compositions. In our billion-year future, this cosmic recycling will have accelerated and intensified as stellar evolution reaches new phases throughout our galactic neighborhood. Consider the hydrogen in water molecules that once filled Earth's oceans. As these molecules escape to space and are broken apart by solar radiation, the hydrogen atoms begin individual odysseys that could carry them across the galaxy. Some will be swept up by the solar wind and ejected from our system entirely. Others might be captured by the magnetic fields of gas giant planets, becoming part of their extended atmospheres for millions of years before being released again. This atomic diaspora reveals something profound about the nature of identity and continuity. What we consider to be permanent substances are actually temporary arrangements of wandering particles. The iron in your blood has traveled an unimaginable distance through space and time, and it will continue that journey long after your brief biological moment has passed. But matter doesn't travel alone through this deep future. Energy accompanies it in forms, both familiar and exotic. The heat generated by radioactive decay in Earth's core will continue warming our planet's interior for billions of years, though at gradually diminishing rates. This thermal energy will still drive geological processes, creating convection currents in the mantle that push and pull on the transformed surface above. Magnetic fields will continue to play crucial roles in shaping the environment of our future solar system. Earth's magnetic field generated by the motion of molten iron in its outer core will have evolved significantly over our billion-year span. The field strength may have varied dramatically, perhaps reversing polar